Good morning, students. We were discussing with work power energy, and in our last class, we discussed about mechanical energy mainly, and there we obtained one expression for kinetic energy of a body, and it was if a body of mass A is moving with velocity v, then its kinetic energy was obtained to be half mv square. We also derived the expressions for potential energy of a body in two different cases. One for gravitational potential energy of a body, that is when a body of mass m is raised to a height h against the force of gravity from the ground or with respect to any reference frame or reference level, then its gravitational potential energy was obtained to be mgh. We also obtained one expression in case of elastic potential energy, where if a spring having its force constant or spring constant K was elongated through a length or expanded through a length x, then its elastic potential energy was obtained to be half kx square. And we had some other discussion in regard to kinetic energy and potential energy of the body. In regard to energy, in mechanics, one important principle is there, that is known as principle of energy. You should remember while we solve the numericals from laws of motion, particularly in case of two problems those were solved in our class, there we mentioned that those may be done using the principle of energy. You are familiar with these conservation laws from your earlier classes as well. One is law of conservation of mass and another one is law of conservation of energy. Today we will discuss a bit about law of conservation of energy. What does it state? It states that the total amount of energy in this universe is conserved. Energy can neither be created nor can it be destroyed. Only transformation of energy from one form to other is possible. That is a very important principle in case of discussing mechanics. That is, we cannot create any energy nor can we destroy any energy. Though in the present context we know, or in the present situation we have come to know, that neither the law of conservation of mass nor the law of conservation of energy are considered to be true or valid individually. Because in some cases we have seen that interconversion between the mass and energy is possible. Mass can be converted to energy, and from the famous equation E is equal to mc square, we can say that if m amount of mass is totally converted to energy, then E amount of energy will be obtained, where E will be given by m into c square. To speak practically, we know with the advancement of science in nuclear physics, high energy physics, we have come to know about different changes where there is some amount of mass which is not accounted for after the change. For example, nuclear fission or nuclear fusion. These two types of changes are very importantly discussed in physics, and those are considered to be very good sources of energy as well. In the coming days, those may also be used for the sources of energy for human use. Already in some countries those are being used. Therefore, instead of having separate law of conservation of mass and law of conservation of energy, today we will talk about law of conservation of mass and energy. That is, the total amount of mass and energy in this universe is conserved. Interproportion between mass and energy is possible. and one is equivalent to other. When this sort of conversion occurs, then one is equivalent to the other. Now we shall see that as in this chapter we are particularly emphasizing on mechanical energy, we will see the practical application of this law of conservation of energy to be more specific in case of mechanical energy. We shall take up a situation, a case, which we also call as principle of energy. This theorem may be stated in this way: that if a body falls freely under acceleration due to gravity from some height, then its total mechanical energy during the fall remains constant. We can easily show it, we can easily prove it. What we have done here, first of all we are going to discuss it about for a free falling body. Suppose a body of mass m is there at a height of h from the ground. Then it is allowed to fall freely, and it will fall following this path AC. We shall try to show that during this fall, its total mechanical energy is remaining constant. At the point A, the body was initially at rest. Therefore, its kinetic energy will be 0, half mv square. So half into m into 0. Therefore, kinetic energy is 0. Its potential energy, we know, as it is at a height of h from the ground and its mass is m, and if g is the value of acceleration due to gravity there, then we can write its potential energy will be mgh. So its total mechanical energy will be 0 plus mgh, that is equal to mgh. Now it is falling freely under due to gravity. Suppose it has fallen through a height x and it arrived or reached the point B. And then its height from the ground is obviously h minus x. So at B, its kinetic energy is half mv square. Now we know v square is equal to u square plus 2gh. And as it is falling from rest, so it is 0 plus 2 into g into x. So if I put v square is equal to 2gx, then I get kinetic energy equal to mgx. And potential energy of the body at this point will be obviously m into g into h minus x. So total mechanical energy of the body at the point B will be given by its kinetic energy plus its potential energy, which comes out to be mgh. So what do we see? At the point A, the body had its total mechanical energy mgh. At the point B, its total mechanical energy is again mgh. And interestingly, we should note that we have calculated its mechanical energy as it falls through a height x, but this mechanical energy is coming out to be independent of x. It does not depend on x. It is independent of x. That means whatever be the value of x, it will come out to be mgh. Therefore, from here only I can say that as a body falls freely from some height, its total mechanical energy during the fall will remain constant. If we are interested, we can find out separately at C. What we shall get at C? Its kinetic energy is equal to half mv square. That is equal to half m into 2gh. That is mgh. And potential energy is equal to 0. So mechanical energy is equal to mgh. We can easily conclude it from these steps because the total mechanical energy has been obtained to be mgh. Therefore, what we see when a body of mass m falls under acceleration due to gravity freely, then during its fall, the total mechanical energy will always remain constant. As it falls here on the ground, this mechanical energy gets converted to other forms of energy. What we see here, as it is falling, gradual conversion of potential energy to kinetic energy takes place. When it was at the highest position, its total mechanical energy was in the form of potential energy. Then it is gradually converted to kinetic energy. Here it has partly potential energy, partly kinetic energy, and when it is just going to strike the ground, its total mechanical energy has been converted to kinetic energy, and when it strikes, we can see some amount of sound energy will be produced, some amount of heat energy will be produced. It can produce some deformation here, that is some amount of mechanical work can also be done, or it can even penetrate some dust to the ground. That's how the mechanical energy is used. We are doing it in this case, but we can also show that if a body falls or rolls down along an inclined plane, then also its mechanical energy will remain conserved. Suppose instead of falling freely under gravity vertically downward, if it is rolling down an inclined plane, then also its total mechanical energy is remaining conserved. And if a body is, suppose I am throwing it in this direction with some velocity v, then we shall see it will follow a path like this. We call it a projectile motion. And here also we can show that its total mechanical energy during this trajectory, during this motion, is remaining conserved. So from this we can understand very well about the application of law of conservation of mechanical energy. And we have discussed about all this, and we should go through it very well. And this will complete the chapter of work for energy. And we have number of numericals to solve from this chapter. Once you prepare it properly, then we shall go to the numericals. From here, we can also have some type of questions that suppose two bodies of different masses are having equal linear momentum, which one is having greater kinetic energy. That is, suppose this is the body of mass M, this is the body of mass capital M. They are having equal linear momentum, that is mv is equal to mv. So kinetic energy of the lighter body divided by kinetic energy of the heavier body is equal to half mv square by half mv square. That is equal to mv into v divided by mv into v. That is equal to small v by capital V. And from this what we get? Small v by capital V is equal to capital M by small m. That is equal to capital M by small m. So what do we see? Kinetic energy of the lighter body by kinetic energy of the heavier body is greater than 1, because capital M is greater than small m. Capital M is greater than small m. Therefore, we have to obtain here is the kinetic energy of the lighter body is greater than the kinetic energy of the heavier body. You should do the reverse one. That suppose two bodies are having equal kinetic energy, their masses are different. Which one is having greater linear momentum? Okay, try to do it. Go through the chapter very well, understand it, and in our next class we shall come with numericals from this chapter. Till then, all will be very good day. Thank you all.